Hi, welcome to the next part of this video. In the previous part, we tried to understand the address mappings, and now I had some discussions, and there is a pretty cool link that was sent to me. And here in this link, you can see all the address mappings of the Agilex 5. For example, here UART. We can see here the address mapping of the UART. This is pretty cool. If we click here on UART, yeah, we can see the base address, the end address, the base address at UART 0 and UART 1. And this is great. But the other method we did through going to the Agilex5 DTSI file is also valid, because here the addresses are also mapped, and in our Agilex5 we included these, let's say, information from Intel Altera to our own DTS file. And this DTS file is for the Agilex5 board. And yeah, the configurations of the base DTSI are used here within this file. But also this page is pretty interesting. Here one can see all the components and their addresses. And now in this part there is a pretty interesting video that was also given to me, and I would like to check this video to understand a bit more, because here the software flow of the Intel Agilex5 FPGA is described, and I just want to a bit more understand what is done here under the hood. If I see something interesting, I will continue the recording and show that part to you, but now I will watch this video. Okay, that was pretty quick after a couple of seconds. Yeah, I'm working as a field application engineer at electronics, and I have a bit more information on what is going on currently within Intel and Altera. And one thing Altera is doing is having this Agilex family, and this Agilex family consists of Agilex 5, Agilex 6, Agilex 7. Let's see if the slides are here. No, Agilex 5, Agilex 6, Agilex 7. And depending on the use case, the Agilex 3, for example, is a bit more low-end FPGA, the Agilex 5 mid-range, the Agilex 7 high-end FPGAs. And that's the whole idea behind this Agilex. But other than that, all these other FPGAs are also relevant. They have their product niche, their market niche where they are good. And the new FPGAs, the Agilex family, let's say, has different types of FPGAs, and one of them is the Agilex 5, which is this one we are working now. But there is also the Agilex 3 FPGA. And let me see. Yeah, I will do a video also on that. Okay, now let me see if I can find something. Okay, the product table is publicly available. The Agilex 3 begins with 25,000 logic elements FPGA and goes until 135,000 logic elements. And you can already see a bit that this FPGA is below the Agilex 5. Let me see if I can open the product table of Agilex 5. Okay, this is the Agilex 5 FPGA page. And here the Agilex 5 consists of two categories, the Agilex 5D and the Agilex 5 Echo Delta. And now I will open the product tables for these both FPGAs. Okay, these the more high-end FPGA, like in the Agilex 5 category, the D one is the more powerful one. And you can see it starts with 100,000 logic elements up to 650,000 or 40,000 logic elements. But now let me open the Agilex 5 Echo category. And by the way, the FPGA we are using currently in this lab is the Echo series. And here it starts also with 135,000 and goes up even more. But the E series, I can tell you, it is a more energy efficient variant of the Agilex 5. The Delta variant is a bit more high power variant with a higher fabric speed. Can we see the fabric speed? Hertz, megahertz. Oh, yeah, it has a bit more fabric speed. The other one, we cannot see it here now, but I can tell you this. Yeah, okay, here it starts with 50,000 logic elements and so on. But this is just a very side note. I don't want to invest more time in it. You can check out the product tables, and yeah, if you have some questions, you can also write into the comments. But now I will continue watching this tutorial. By the way, the rocketbots.org is pretty nice. There you can find a lot of tutorials for this SoC stuff. But this will change. I guess they will move to GitHub. But you should also see more information on this in the future. And if I see something, I will also share here. But they will move to GitHub. Okay, very funny. Here you can see again the DTSI file which is included, and here they again reuse the components defined in the DTSI file. This is what we found out. I guess this is the example of Stratix 10, and for Stratix 10 there should be also some documentation on all the addresses. Okay, nothing interesting. Okay, yeah. Nothing interesting in that video, which is relevant for our work. Okay, close this. Okay, let's continue. I want to search something in the Agilex5 documents. Grep -R. What is the SMP? I would like to understand this. Then gibit UG68. Not get it. gedit, or how you call it. Oh, what's the PDF tool? Firefox. Firefox. Good. SMP. Okay, no SMP. How can I search for complexity? How to search in a folder in PDFs in Ubuntu terminal. PDF grep, okay. Yeah. With this I can better search in my documents. I love Linux, that's so easy. Incredible. PDF grep SMP minus dot is meaning this is a directory. Yes, I would like for you to search in this folder. Okay. Okay, that took too long. Wow, very interesting. SMP boot Agilex5 FPGA. SMP support. Yeah, this is the Altera GitHub page. Now you can note rocket boards is this one, and this is now this will be legacy in the future, what I have heard, and this thing will be the new standard. And now SMP driver, okay. SMP. What was SMP? It is an abbreviation for something. ChatGPT. What is the meaning of SMP? So what is SMP? Symmetric multiprocessing, which is blah blah blah. Multiprocessors share the same memory space and have equal address system. In an SMP system, each person works on its own tasks, but can also. We talk about the SMP. It means that Zephyr, an open source blah blah designed for medicine, is capable of running on systems that have multiple processors. We have multiple Zephyr real-time OSs that can run in parallel and do stuff, and they can share all the same memory. Okay, cool. What I've heard is that the new Agilex5 example we are using here will also support SMP, but this will come out soon. I talked with the guy who built that example, and he gave me this link, and he also mentioned on this SMP thing. Okay, now we've done this. I would like to continue on the journey of understanding this SoC, and there is something I would like to understand a bit better, the DDR mappings in that example. But before starting with that, I will take a tea. 1 second. Okay. Let's close this. Let's close this as well. Open this. Now what I would like to understand is I would like to understand the DDR mappings, how this is done, because this is more a Linux thing. But for example, how the DDR memory space is mapped into Linux. Let me show you an example. There is a file, this thing, somewhere, this. And if I open that slide, we can see we have a global address map for the whole HPS. And for example, here in that region, 128 megabyte PSS peripherals is the UART mapped. But here we have other addresses that are mapped to specific functions. For example, the HPS to FPGA bridge has this address, but here we have this address, and here we have this address again. Therefore, I would like to understand how this whole addressing is done, really under the hood. But let us program for this. The device, I will delete this. I will start the programming process. I hope it works. Yes, it works. Now Linux should boot. this friend. Port, yes. Oh no, there's something wrong. Let's do it again. Port, yeah. This. Yep, it works. I'm logged in our Linux, and now if I do ls, I can see here multiple tests. There is an Ethernet test, there is I2C test. What's that about? I2C test. What? What's this file about again? Here, open it again. No. That's what is going on. Here. Ah, if I click on cool. Okay. Yeah, I don't get it. Clear. Okay, here. Good. Okay. Okay, I have no clue what is done here. Okay, there is this component max13760. Let's open that. Let's open that. Okay, this is a PWM fan control. I guess this component is on our board. Let's open a terminal, change to Agilex5 docs, PDF grep, and then paste this friend here. Let's see if this is somewhere in one of our documents mentioned. Yeah, your 19 fan control. Open this thing. Yeah. Okay, I don't get it. Bus I2C address hexadecimal 57, and this is the fan control. This is the part number. Now the question is, what is this LED doing now? Yeah. Okay, let us see in QSys how this is met. AXE5-1. Clock input, clock output, conduit, and what was the internals of this thing? Okay, there's an interesting document on that I2C stuff. I would like to read this. We can read it together. I want to see it in a single page width. No. Can I change this for? I don't like this 2-page view. Save. Open the folder. Document view. Better. Okay, this is not an Agilex5, but I guess the idea will be the same. That's also an Altera, Intel Altera FPGA. Okay, very interesting layout. Okay, I will stop and then in interesting pages, interesting sentences, I will continue and show it to you. This is a Cyclone 5 FPGA. Basically, the idea for the Agilex5 FPGA is the same. Let me show it to you. Yeah. HPS to fabric, goes to the NOC, and from the NOC goes to the level 3 cache, and then to the processors. Here, bridge, level 3, they call it L3 interconnect main switch. I guess that's the same like NOC. And then here MPU, multi-processing unit, I guess. ACP. ACP. Yeah. Good. Let's continue. By the way, we have done the same in our lab. Let me show it to you. Wow, what's that? Close. If we see this here, yeah. The first stage bootloader of the U-boot is included into the programming file, which then is executed, and then this thing in like the main loading system then executes the whole stuff in the SD card and loads that stuff. But the first stage bootloader is this mini U-boot here. Let me see if I have this here also in our scripts. Yeah, here, this is this thing. This also includes the ARM trusted firmware binary blob. Oh, that's here. That's not, that doesn't include this. Okay. No. But what? I make a symbolic link to the BL31 bin. Then I do some patching to make things work. Then I convert this thing, u.bin. Where do I create this? And here I do the make. Then I check if this file exists. I copy that file. I change it to iHex. And that's it. And here is the u-boot script. Here I do the kernel. Here I do the kernel.itb. The kernel.itb includes the ITS file. In the ITB, what was the ITS again? Fit kernel ITS, what was this? Ah, okay, the .its file includes the kernel, then the FDT, which includes the device tree blob, which is the compiled device tree for the kernel to understand the addresses of the peripherals and stuff. And this is the configuration. Kernel signature. Aha. Okay. But this mini U-boot is here. Where is it? This thing. This is the mini U-boot. Okay. this. The device tree includes also the addresses of the bridges. Interesting. Let's see if I can find this here. Wow. Okay, this is the device tree block. Open a new tab. And this, search for bridge. Now F2 S. Wait, this must be here in this link as well. Yeah. Yeah. Here we have 256 gigabyte, 240 gigabyte address range. And these three combined gives us 256 gigabyte address space for the HBS to FPGA bridge. Very interesting. And this is then mapped to interesting. By the way, this signal is exactly the same signal like here. .oe here. It's output enable, I guess. Aha, the Agilex5 has also the scatter gather DMA. And the other DMAs, after each transmission, they do an interrupt, and then the CPU decides what to do. And in the meantime, the FIFO gets filled by the camera. And the scatter gather DMA has descriptors, uses preloaded instructions called descriptors with information about the transfer, and then the scatter gather DMA does all the transfers and stuff without taking too much time and filling the FIFO. Interesting. Okay. Okay, I read this documentation of this. No, it's not documentation, it's a bachelor thesis. It's very interesting. I recommend it. You can find it on Google. Okay, continue with our work here. What I'm thinking of is to create hardware probes and to scan what is going on under the hood and to understand really which signals are executed and how it's being done. But I have an idea. If this thing works, I2 square get. Is this a function provided by Linux community? Do I have it here as well? No. Okay. I2 square get. Aha. Interesting. Let's execute this on my PC. Cool. Okay. That's okay. With ptrace we could trace the kernel, what it does. Okay, but interesting. Now the question is, what should I do? Should I write some C code with hardware level memory mappings to execute some instructions and see what happens, or how should I further dive into this whole system? How should I do it? Especially these RAMs, I would like to understand how. I guess I need to compile a C code to mmap and then address this stuff. Okay, the idea is I would like to further use this bridges and blah blah blah, and for this I need I want to use this bridges and so on, and for this I need somehow address to the hardware addresses, to the physical addresses, and I can use this with mmap. So I could write a C code with mmap and then, you know, access the stuff. What I could do is I could write a C code with mmap and then I could write a C code with mmap, then address a certain address space and then print it. For this I need to write a C code, compile it, and then execute it. I have the ARM GCC compiler. Okay. Yeah, let's try it. Let us try this. But there is an issue. I need to transfer the file to the Linux. I need to transfer the file to Linux. How can I do this? I could open an SSH. Let me see this. Let me see if SSH runs here. System control. No. Let's start. Oh, let's start. Yeah, okay. It listens to 22 and 22 is SSH. Good. I can use SSH to connect to this friend, but for this I need an Ethernet cable and a USB to Ethernet adapter for my Ubuntu. Let me think. Let me think if I have something like this. 1 second. Okay, I have USB Ethernet should have a fixed address. And I need to set the address of this friend. Link is up. Good, I need to set an... I guess that's the address. Yeah. Huh. Yeah. Ha ha ha. This is this machine. Applying. Connection refused. Yeah, group login should work. Yeah. Public key authentication is committed. Permit empty passwords. Okay. There is some issue with the connection. Usually now if the connection is there, this thing shouldn't work because this should now block. No, this shouldn't happen. There is no connection between my machine and the Linux here. No. Okay, now it should work. Yeah. No. Good. Okay. This was a pain in the ass. Now it works. this is the loopback. I was using the loopback. This thing has no address. Oh. Okay. IP addr at 10. What was my address here? Two slash 8 del ETH 0. Now it works. Now I should have SSH. I have to set net mask to 8. Okay. Okay. Now this is my default gateway, and this is the address of the board. No, no. Yeah. Okay. I need to make this static here because otherwise. Now let's see what will happen. Hmm. Good. Now I will see if the address is not properly set up. Ah, oh nee, not DHCP. I need to use static inserts, static address, net mask, gateway. Quit. Okay, now I would like to wait. Okay. Right. Now. Oh, let's reboot. Okay, now it works. Now after every reboot I have my SSH. Good. After having this SSH, question is if I have the file transfer protocol. What was the file transfer via SSH? SCP. SCP? SCP? Yeah, I have SCP. Great. Because now I can compile my code and write a script to compile my code and then transfer it via SCP to the embedded Linux. And on the embedded Linux, then I can do my mmap tests. This is good. Okay, now create This is a very interesting operator, meaning always if I get the 16th value, I do a new line. Nice. Munmap. Okay, now compile this. GCC, this one. Okay. Okay. Great. SCP main root at what was the address? Is it? It's 10.0.10.10. Folder is home root. Home root. Oh, geil. Okay, nice. One, two, three, four, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 16. Okay. Nano main.sh. This is my script now to compile everything. Go to chain source file, output file, roots, path, echo compiling source, GGC torsion, output file is this, source file is this, compilation successful, yes, remote path is this, nice, okay, great. Great. Great, great, great. Now I can do a nano. And let's see. Now I would like to read this thread. Memories. I thought there was a syntax somehow to write it like this. No, but it didn't interpret it like this. Okay, this is not a valid syntax. Okay. If I use the SDRAM address space, I should be able to write. If I can execute it. Okay. Something is going wrong. Oh. I wrote somewhere I shouldn't wrote. Okay, nice. It couldn't write. Something happens again. 8,0,0,0 and then 1,2,1,2. Bus error. 0, 8, 8, 1, 2, 3, 1, 2, 3, 4. 0, 8, 8, 1, 2, 3, 1, 2, 3, 4. Bus error. That could be the case because the secure device manager might prevent it. What happens if I what happens if I use the address 0, 0, 4, 4, 1, 2, 3, 1, 2, 3, 4. Here it works. The red ones I can use. The blue ones I cannot use. Why? And MP. I have an idea. I would like to write here in QSys we have these friends. Peripheral subsystem LED. And I would like to write into these, and I guess there is even a code somewhere to write into them. No. Can't HBase test. We can write into these things. We can write into these friends. Lightweight HPS to FPGA. Now we just have to understand the right address. What does the this is the address this is the address of the lightweight HPS to FPGA. Now the question is what the address of these guys is. Zoom out, EMF peripheral subsystem, zoom in. Yes, this is the address. SysID. What's the SysID? Dead beef. If I read the address 000, if I read the offset, I should get dead beef. This is very interesting. What is this here? I would like to read the size of the memory 16. And I would like to read this only, and I would like to print it. Now let's see what will happen. No dead beef. I should be able to read this because this is here. What does the schematic term mean? Bridge data symbol address whips. Now what I would like to do, the base address is this. Then I have to add this. Is that right? You know what I can do? I can read just a bit more. Let's say I would like to read 160. because then I should be able to read. Okay, no dead beef. That's not good. No dead. No dead beef. Okay, what I want to do now is it should be able to read. Should be able. If I look to the address map, I can see. Wait. I can see this guy is mapped to the base address 0 and the SysID includes deadbeef. Meaning if I read this address I should get the SysID deadbeef, but I don't get it currently. And to be able to understand why I don't get it, I want to insert here some probes to see the read instructions on that Avalon memory mapped bus. And to do this, what's that? Yeah, and to do this, I need to work a bit, and I have to research a bit on how to add this thing. Okay, let's close this. Let's open this kind of tools. Ah, shit. Stop. No. Now what this thing does, it should compile it, and then I should have the logic analyzer, and then I can see what the bus is doing underneath. Okay, that's it for today. I will continue in the next video because this will take some while. Thanks.